It's going to be important for you to take some detailed notes over what we discussed today, because we will be doing a lab beginning next week that is dealing with the ideal gas law. Remember the PV equals nRT that you've been doing on WebAssign. We're going to have to deal with pressure here. So we're going to discuss now Dalton's law of partial pressures. If you can look at the diagram here, here's just one way that we could collect a gas by water displacement. You can see that whatever this pink gas is, it's running from a tube up, displacing the water from the container. All right? So we could collect the gas. We're going to do something, we're going to use what we call a eudiometer. We'll introduce you to that maybe tomorrow. It's a piece of equipment that we use one time a year, so I'll have to get those to put those out. But we're going to use water displacement to collect the gas. Now, let me move my little box here. If you look here, mixtures of gases require special handling when we do calculations. The reason being, if you see up here in the gas, the pink represents the gas that we are collecting. The little blue circles represent water that is evaporated in that gas. So, we have two different types of pressure. We have pressure from the pink gas, and we have pressure from the evaporated water. Okay, pressure from the pink gas, pressure from the evaporated water. So, if I would come up with an equation for this one, that equation would be the total pressure is equal to the pressure of the collected gas, in this case represented by the pink circle, plus the pressure of the evaporated water. Now, if we would have more than one thing, if we would have more than one, could we go P sub 1 plus P sub 2 plus P sub 3? Yeah, we could. We could have as many partial pressures as whatever is dissolved in that gas. Okay, in this case, we only have the gas collected and the water that is evaporated in there. So P total, the total pressure, is equal to the pressure of the gas collected plus the pressure of the evaporated water. Now, if you look, you will have a demo that you do tomorrow. Okay? We will not, this was actually your pre-lab you will do tomorrow, and it will be with this particular experiment right here. So, what is happening is they are taking sodium chlorate, okay, NaClO3, solid. They have it in the test tube. They heat it, okay. Well, we know that the decomposition, okay, If we go way back and I look at my help sheet here, this is a decomposition of a metal chlorate. So a metal chlorate heated gives me a metal chloride and oxygen. We have a balanced equation here. My metal chloride is going to be sodium chloride, and oxygen gas will be collected in this bottle right here. As you can see, they've already collected one bottle full of oxygen, but that oxygen has, if you remember, that oxygen also has water vapor with it dissolved in this bottle. All right, so we're going to have to account for the pressure of that water vapor. All right, I don't think we might have used potassium chlorate. We did this, lab. We did this. We just did not collect the gas. Okay, we did the decomposition, but I think it was potassium chlorate, not sodium chlorate. Okay, so here's the setup that we would use to collect that gas when we heated it. All right, could we take the mass of the sodium chlorate that we had and use the law of conservation of mass, measure the mass of sodium chloride at the end, subtract the two, and get the amount of oxygen? Could we get the mass of oxygen by doing that? Absolutely. Okay, based on the law of conservation of mass, the products and the reactants have to have the same mass. So we could determine the amount of oxygen that was driven off in this. Here is what we would do to get the pressures. The total pressure, the PT, would be equal to the pressure of the oxygen plus the pressure of the water. So the total pressure would be the pressure of the oxygen plus the pressure of the water. Now, based on Dalton's law, okay, here we have P1, here we have P2. Now, as I'm looking at that, the volume is constant, the temperature is constant. So, that's why we can use this equation. The P total equals the P1 plus the P2. Because based on Dalton's law of partial pressures, we haven't increased the temperature. They're in the same area. We haven't increased the volume at all. If you look at this diagram here, this will be provided to you. But what this is, if you look, it is the relationship of water pressure at various temperatures. So up in that blue box, up at the top, it says the pressure of water vapor at various temperatures. You can see what happens to the water pressure as we have an increase in temperature. The water pressure also increases. Now, if you look, could you tell me the pressure, the water pressure of this, let's say the water pressure at 25 degrees Celsius? Could you do that? Well, all you have to do is be able to read a chart. Okay? You could read a graph. Okay? But I look here at the chart, 25 degrees Celsius, the water pressure in millimeters of mercury is 23.76. What's the water pressure at 70 degrees Celsius? Well, 233.7. We can't see it here. Let me move this. See where it is? 760. 760 millimeters of mercury at 100 degrees Celsius. So that's where our lines up here bring us to. So to determine the water pressure, we need to, let me check that, the water vapor pressure, what do we need to know? The temperature. So if I would have the temperature of this room right now, could I determine what the water vapor pressure was in here? Absolutely. Okay, absolutely. I'll come over here to my little thermometer. It's telling me that we're reading right around 73 degrees, somewhere around pretty close to 23 degrees Celsius. So if I look at 23 degrees Celsius, you know, could I set up a proportion to get a very exact number? Yeah, I could. It's going to be 23, let's say that's about halfway in between 25 and 20. So what's halfway in between 17 and 23? About 20. So somewhere, just guesstimating, somewhere around 20 millimeters of mercury. All right. So based on this water vapor, all I need to do is have this chart with the temperature, which I will give you one when we are doing this lab. So if I rearrange, and this is the important one right here, folks. This is the important one. I'll give you a second to write it down before we talk about it. This is the important part of. This is an important part that you will be using when you do the lab next week, okay? By rearranging the equation, we said that the total pressure was equal to the pressure of the gas collected plus the pressure of the water vapor. Well, if we rearrange, we can solve for the pressure of the collected gas. So P of the collected gas is equal to the total pressure minus the water vapor pressure at the specific temperature. So if we know the temperature, we can read the chart to get the water vapor pressure. All right? How are we going to get the total pressure? Okay? How are we going to get that total pressure right there? Well, how you are going to do it is when you do this lab, you are going to get onto this nice little place here. It's called the internet. And you can get on weather.com. And I can even come up and say, all right, whatever. Okay? Just give me, okay. I can come in here and I've got Seatown already up. So as I am looking here, on this site, it's telling me that I have my pressure going down, but my pressure is 30.48 inches. What that means right here, that 30.48 inches of mercury. I'm going to walk you through here in a second what you're going to need to do, because obviously we have a problem with our labels, don't we? What is our water chart in? Okay. What did we just say that the water was in? Anybody remember? Millimeters of mercury. We've got inches of mercury given here. So we need to do some sort of a conversion, and I'm going to walk you through that here in 1 second. But we're going to just talk a little bit. I'll try to blow this up a bit to see if we can see it any better for those of you that are in the back. Okay. Now, here we go, and this is just some background information you will get here in a second. But if we read through this, it says the standard temperature and pressure. Remember, we've dealt with STP, and we know that STP is standard temperature, 0 degrees Celsius, which corresponds to 273 Kelvin, and a pressure of 1 atmosphere. Well, at that temperature and pressure, it is equal to 760 millimeters of mercury. Okay, so 760 millimeters of mercury is the standard pressure with that unit, with that label. The ideal gas law can be used to estimate the molar volume. If you remember, PV equals nRT. If we rearrange and solve for volume, volume is equal to the moles, the ideal gas law constant, times the temperature all over the pressure. Substituting those values in, okay, the 1 mole of the gas at the ideal gas temperature, okay, and the ideal gas constant, 0.0821 liters times atmospheres over moles times Kelvin, multiply it by 273 Kelvin, divided by the pressure, 1 atmosphere of pressure, we get 22.4 liters. Does that sound familiar? Does that sound familiar? Isn't that the molar volume of a gas? 1 mole is 22.4 liters, right? There's the calculation. You can do the math if you want it. Okay, you can do the math if you want to, but it's all right there. Okay, it's all right there. So this 22.4 liters is the accepted value for the volume of a gas, volume of 1 mole of a gas at STP. Now, it's talking about the cylinder that is filled with water. You can see, here's Dalton's law of partial pressures that we just talked about, okay? Where we said that the individual pressures, the P1, the P2, the P3, P4, P5, if there's that many, all of the individual pressures add up to the total pressure. Now, how are we going to use this? Okay. Here's the chart. We've already talked about that chart. I want you to read this while I go get her. Let's check this out. Let's write this down. Okay, it says, to calculate the molar of a gas at STP experimentally, you apply the combined gas law. Now, it's probably a good idea to write the combined gas law down in your notes now. And that is P1 V1 over T1 is equal to P2 V2 all over T2. It says right below it, the variables with the subscript 1 represent the condition measured during your experiment. The variables with the subscript 2 are STP conditions. To get the molar volume at STP, you would then divide the value of V2 by the moles of gas N. That would give you a theoretical volume that you produced in your experiment. So, okay, so basically what we're saying here is anything with the V1 is the experimental one. Anything with the V2 is the STP. Could we find the pressure of a gas, determine the volume of a gas experimentally, and use the temperature that we have in the room? Could we get that experimentally? Absolutely. And we are going to use that then to do this calculation to solve for V2. So, here is the question that we are going to go through. I'm saying that what I'm going to do